Welcome to IGLUNA 2021 field campaign. Welcome from the top of Mount Pilatus in Lucerne, Switzerland. IGLUNA is the ESA Lab at CH, part of ESA Lab initiative launched by ESA to create a hub for innovation between universities, research organizations, and industry. Space Innovation coordinated the 12 teams from all over Europe and even Canada participating to the IGLUNA 2021 adventures and led the main systems engineering activities. I have the pleasure to introduce today the live stream of the IGLUNA team PowerHab of Strathclyde University in Glasgow, Scotland, UK. The PowerHab team worked on and will present a very relevant topic as well for space as for Earth: energy production, storage, and distribution. Please enjoy their presentation. The team will answer your question after the presentation. Do not hesitate to post them on YouTube.
Hello, and welcome to the P12 PowerHab presentation for the IGLUNA 2021 field campaign, brought to you, well, from my kitchen. I'm Callum, the student team lead for this project, and as such, I'm sure I can say on behalf of the whole team how very disappointed we are not to be there in Switzerland with you. However, we are excited to bring you our innovative designs, prototypes, displays, and studies which fuel the possibility of powering a future human lunar habitat. But first, what is PowerHab? I think it best we head upstairs to the office to find out more. So here it is, where the magic happens.
Throughout the year, myself and the team have been working remotely at setups like this to further the PowerHab mission statement, which is to design a resilient power generation, storage, and distribution system which meets the power demands of all subsystems of a lunar habitat and demonstrate technologies required for this power system. However, this is a very wordy, confusing description of our project created to satisfy our stakeholders at the University of Strathclyde. So let's take a look visually at what this actually means. This is what we call the graphical abstract for our project, and is essentially an overview of all our system concepts required to create a robust lunar power system. There are three main categories of power system technologies that we have investigated, including generation, storage, and distribution. Our main power generation source will be from solar arrays, both on the lunar surface and in lunar orbit aboard a solar power satellite. This main generation will be backed up by both hydrogen fuel cells and small-scale nuclear fission. The main technology for power storage involves lithium-ion batteries, not too dissimilar to those used in modern electrical vehicle design, and this is supplemented by a thermal mass storage system. Further, with the correct setup for water and hydrogen storage, the fuel cell can be reversed and used as a further storage system during times of excess power generation. This year's project is a continuation of past PowerHab developments, and as such we have selected a few of these key technologies to further develop. This includes prototypes for the wireless power transmission system via the use of lasers and the proton-electron membrane hydrogen fuel cell. This is combined with a complete solar power satellite design including specific orbits and a small-scale nuclear fission feasibility study to round off our project this year.
But we'll get to all that in good time. First, let's head out to the lab to discuss wireless power transmission in more detail.
The solar power satellite is required for a stable power generation system, as the ground solar arrays during some months are only able to generate power 50% of the time. The SBS generates its power through two large deployable arrays, and this power is then channeled into a continuous wave fiber laser to beam power to the lunar base. A trade-off analysis was performed to select the other onboard SBS subsystems. A lithium-ion battery is used to power the SBS critical systems when the SBS is eclipsed. Star cameras are used for course and laser attitude determination, and sun sensors are used to orientate the solar rays and the radiators. Radiators are used to dissipate thermal energy in order to keep key subsystems within operating temperatures. Other onboard systems include communication antennas and the onboard computer. Based on existing subsystem specifications, a mass budget was performed. The radiators were sized through a single-node thermal analysis performed for a hot and cold case scenario. Assuming a 20% safety margin, the dry mass of the SPS is just over 4 tons. Based on an existing subsystem specifications, a power budget was performed. The fiber laser is the most demanding with a 100 kilowatt power requirement based on a 75% plug-in efficiency. The total power requirement, considering a 10% safety margin, is just under 125 kilowatts, and therefore the solar arrays should be sized accordingly.
To complete this sizing, first a solar cell selection trade-off had to be completed. A quadruple junction solar cell was selected as a COTS component produced by the manufacturer Azure Space. The model 4G32C provides a best-in-class ball efficiency of 32% and an end-of-life retention of 0.90. The solar array sizing calculation was then performed in accordance with NASA and ESA standards and was designed for the 125 kilowatt power requirement at end of life. The calculation shows that the array requires a minimum size of roughly 538 meters squared. This requirement shall be met by 2 planar solar arrays deployed by the SPS, and for a regular hexagonal design, this will require a side length of roughly 10.2 meters. The following deployment animation has been made here and shall be integrated into the final display of the solar power satellite. As part of the deployment optimization, the following metrics were produced for this deployment. The stow to deploy diameter ratio was found to be 4.38, with the height of the stowed array equal to 3.63 meters. The results here comply with constraint requirements detailed in the final report to ensure the feasibility of launching such a design within the current constraints of launch vehicles.
When creating the wireless power transmission system, it was important to consider a method to coincide with the SPS and prototype design. This table shows the trade-off between 2 different far-field techniques, microwaves and lasers, which has been carried out to identify their relative strengths and weaknesses and therefore determine which method would be best to fulfill the project objectives. Using lasers allow a narrow focus beam to be used over large distances, resulting in a small receiver and transmitter size for solid-state lasers. Disadvantages to laser are the safety requirements due to its damaging effects to eyes and skin. It has a maximum convergent efficiency of 40 to 50%, and cooling systems are necessary for high-powered lasers. Advantages to using microwaves are their known high efficiency rates and well-developed technologies. However, safety is a concern as body tissue interaction can occur at microwave frequencies, which is extremely harmful. Microwaves require a large transmitter and receiver area, and interference may occur with close frequencies. Finally, lasers were chosen as they are more beneficial to the overall system design, power requirements, plus the incorporation of beam steering and the use of existing solar arrays. In addition, the reduced dimensions allow to minimize payload mass, and using lasers has also allowed to create a prototype which is more engaging and a better visual representation of the system.
Speaking of a visual representation, I've made it down the stairs to the garage. While it might not have all the equipment we are accustomed to at the University of Strathclyde, thanks to our sponsors, RS Components, I have all the tools required to manufacture the WPT prototype. This included the hardware and software production of the laser cart and the scaled down track which simulates our SPS orbit. The laser shall illuminate the lunar surface solar panel when in view, lighting an LED to demonstrate the wireless transmission of electric power. But the best way to show this is to power it on, upload the software, and dim the lights. A servo motor automatically repositions itself with the aid of a Hall effect sensor and magnet embedded in the track. It then accurately follows the position of the surface solar cell and activates the laser. While the diameter of the moon and orbit trajectory have been accurately scaled down, the size of the SPS system is of course constrained by the size of consumer electronics. However, this prototype demonstrates the effective use of lasers as a means of wireless power transmission. I would now like to introduce you to Rory to discuss hydrogen fuel cells.
Hi, I am Rory Cormack, head of the power storage team with PowerHab. In this section, I will give a brief rundown on fuel cells and how they work, which will be followed by the demonstration of the fuel cell to show the cell as a source of consistent power. After this, the remote control system will be shown, and then I shall discuss why a fuel cell was picked and the advantages that a system like this brings. Hydrogen fuel cells utilize hydrogen and oxygen to convert chemical energy into electrical energy. The reaction process starts with hydrogen being split into hydrogen ions and electrons at the anode. These hydrogen ions are then transferred through the electrolyte to the cathode, where they are combined with oxygen and the electrons, which pass through the external circuit to generate the electrical energy. Along with producing water, this system also produces heat, as this is an exothermic process. With this heat being generated, it reduces the efficiency of fuel cells to approximately 83%. The cell we will be showing today is a 50-watt proton exchange membrane cell, which operates using hydrogen and air to produce the required power. Some notable aspects of this are the small footprint and weight while working at good efficiency levels to produce the required power. All other specifications are listed on this slide. Welcome to the demonstration of our proton exchange membrane fuel cell. Here we have our 50-watt cell, a purge valve, the cell controller, supplemental battery pack, voltmeter, and the compressed hydrogen. One major change was the change to an open-air cathode, which reduced the need for two compressed gases as the cell runs off hydrogen and air rather than hydrogen and oxygen. We'll now turn the cell on. As you can see here, we are producing approximately 16 volts, and this, along with the 3 amps of current, allows us to reach our target of 50 watts, and this is done by using hydrogen supplied at approximately 1.3 bar at a flow rate of 0.6 litres a minute. This shows that fuel cells are a great and viable option for power storage. Thank you for watching.
Cheers, Rory. Hi guys, my name is Rory and I'll be taking you through the remote control aspect of the hydrogen fuel cell system. First off, we have the Raspberry Pi 4B. Now this is one of the main components of the remote control system, as it is able to switch on and off and read data from each component connected to the system. Each of these components are connected through these jumper cables, which is then in turn connected to the breadboard. First off, we have this little component here called the INA 260 power sensor. Now this power sensor is used to monitor the output of the fuel cell. You know, in an ideal world, this is where the fuel cell will be connected to. But owing to the fact that I'm in England and COVID restrictions means that we can't meet up to connect our systems. Fortunately, however, though, I have tested this power sensor and it works just as well, and it works as expected when connected to other voltage supplies. Next up, we have the solenoid valve. This is another crucial component of the system. This is able to shut off the flow of hydrogen going into the fuel cell. Now this is really crucial because if we ever need to shut down the fuel cell, or it becomes an event where it becomes unsafe to continue operating the fuel cell, we can use this component to stop hydrogen flowing into the fuel cell and remove any risk and any danger. It's connected via a transistor, a diode, back to the Raspberry Pi, and is actually powered by this 12-volt battery pack. Now, if the Raspberry Pi wants to switch off the solenoid valve, it can change the base voltage to the transistor, and in turn, the solenoid valve is powered off. Next up, we have a DHT11 temperature sensor. Now, this will be used to monitor the atmospheric conditions around the fuel cell, such as the temperature and humidity. We will be monitoring these values as to see how the hydrogen fuel cell performs in different atmospheric conditions. And it could provide very useful for any future space missions to understand how the efficiency of hydrogen fuel cells is altered. And lastly, we have the sensor-on flow sensor. Now this is used to monitor the flow of hydrogen into the fuel cell. It will be used via the Raspberry Pi and also be used in conjunction with controlling the flow of hydrogen into the fuel cell. If this senses that the hydrogen flow is either too low or too high, the Raspberry Pi will read the signal and then make a decision whether or not to actually control the solenoid valve and switch it off. And then lastly on the side here, we have these two LEDs. They're just used to help the operator understand what's going on with the system. So the red LED means that the solenoid valve is closed and there's no hydrogen flowing into the fuel cell, whereas the green LED is good news. Hydrogen is flowing and electricity is hopefully being produced. So this is kind of the hardware. Obviously, in the fuel campaign, This would have been a much more compact system and it would have been placed inside its waterproof box. But I thought for this demonstration, just at home, I'd like to get it out of its box just so you can see each component just as clearly. Next up, I'll show you how we actually read the data and what it looks like on the screen. Cheers. This dashboard will be used to monitor the hydrogen fuel cell. It shows the hydrogen flow rate, whether or not the hydrogen is flowing, the voltage output, the current output, and the local temperature and humidity. This data is sent from the Raspberry Pi to an Apache server on the local area network. The data is then downloaded from the Apache server and using an Excel API is inserted into this dashboard. As such, this feed is live and is constantly updated as the Raspberry Pi is running. This allows for continuous monitorization of the Raspberry Pi and of the hydrogen fuel cell itself.
A major benefit of fuel cells is the specific power, as they have small size and volume along with lower weight and cost than other options. Along with producing power, the fuel cell can be reversed and used as an electrolyzer to split the product water into hydrogen and oxygen. During times when the cell is not required, it can be used as an electrolyzer to ensure that it has enough fuel to supply the demands of the habitat at any time. As a power storage option, the main competitor would be a battery bank, but fuel cells offer numerous benefits as they allow for easier recharge while occupying less volume and being lighter to allow for easier transportation to the moon.
Hi, my name is Zahar and I'll be going over this year's Lunar Nuclear Fission Subsystem study. This study was used to investigate the viability of adding a small-scale nuclear fission subsystem as a backup power generation source to the existing PowerHab system. This study began with a preliminary investigation to determine the value of adding the subsystem. Looking firstly into the need for nuclear power generation, both the European Space Agency and NASA have deemed space nuclear power systems as essential for future lunar surface exploration missions. Nuclear fission can offer many benefits to a lunar habitat power system, such as high power density, constant power source, and simple system designs providing high reliability. This encouraged the conceptual designing of the subsystem, which started with identifying the technology available. The nuclear power systems considered were radioisotope thermoelectric generators by NASA and the European Space Agency, as well as NASA's kilopower systems. System selection was based on ensuring the subsystem could meet two important design requirements. The first is its purpose, to constantly and reliably supply the baseline power demands as a backup power source used to increase the stability and redundancy of the PowerHab system. The second is a power requirement of at least 20 to 25 kilowatts of electrical power needed to cover the life support systems of a 6-member crew and to balance power generation demands across all PowerHab subsystems. Given these requirements, kilopower systems were chosen as only 3 10-kilowatt systems would be needed. Kilopower systems are small, lightweight and modular nuclear reactors, meaning that the 3 systems needed could be transported on a single moon lander. Looking closer at the system design, 3 subcomponents are highlighted. The reactor at the bottom consists of a high-enriched uranium-molybdenum alloy core used to generate high thermal energy. This core is controlled by a boron-carbon rod and surrounded by a neutron reflector and shielding, which are used together to limit radiation dose exposure. Above is the power conversion system, which uses sodium heat pipes and Stirling engines to efficiently convert core thermal energy to electrical power. At the top is the heat rejection system, which transfers excess heat to the surrounding space environment to cool the system down using titanium water heat pipes and radiator panels. The main focus of the study was investigating the primary safety hazards and feasibility issues involved with establishing the nuclear fission subsystem, thereby evaluating the viability of adding the subsystem. The safety analysis used a hazard risk assessment to analyse the maximum level of risk of potential radiological safety hazards occurring on the surfaces of Earth and the Moon. These hazards were a launching accident or accidental re-entry of a kilopower reactor, leading to the dose exposure of nearby launch site workers and public, and the risk of constant dose exposure to astronauts living and working alongside the nuclear fission subsystem. Safety protocols can be implemented to minimise the probability of these hazards occurring and the severity of dose exposure to individuals. Examples include keeping the core in a cold state from launch until lunar surface operation, designing and employing re-entry strategies, and establishing a 1 kilometre diameter, no occupancy zone around the subsystem. Following all protocols would ensure that the subsystem can be established with no radiological safety concerns. The feasibility study evaluated feasibility issues concerning the practicality and challenges of the kilopower reactor core fuel that must be addressed before the subsystem can be added. These issues describe the threat of high-enriched uranium fuel from a re-engined kilopower reactor falling into the hands of terrorists to be used for nuclear weapons, the limited future of uranium fuel as the demand for uranium rises with the need to decarbonize the global energy system, and the safe disposal of high radioactivity and temperature-spent reactor fuel on the lunar surface. This evaluation classed the addition of the subsystem as overall moderately feasible, as each issue can be addressed by carrying out comprehensive and in-depth planning early in the lunar surface exploration mission design. For example, accidental re-entry strategies can be adapted to prevent any security threats, and a detailed plan on the safe disposal of spent reactor fuel can be produced to consider all impacting factors. This study concluded that adding a 30 kilowatt electrical power nuclear fission subsystem would offer a constant and reliable backup generation source with high redundancy and fault tolerance. The kilopower comprised subsystem would increase PowerHab system stability and balance out generation demands across subsystems. With appropriate safety protocols and planning early in the lunar mission design, the subsystem should be safe and feasible to operate. Overall, subsystem establishment should be viable and is highly encouraged.
So that brings us to the end of our whistle-stop tour of lunar habitat power systems. We have covered a lot of information throughout the past 20 minutes and have even more details available at our website, powerhab.co.uk, including full documentation and final reports generated as part of our Masters project. We thank you very much for listening and welcome any and all questions.
Thank you, PowerHab. Thank you, Strathclyde. Thank you very much for this very interesting presentation. As mentioned in the introduction, it's really a very relevant topic. I'm really impressed by the number of topics you addressed during your projects. I think we have time now for a few questions, so please do not hesitate to post them on YouTube. I take a look on YouTube on the channel. So for starting the question, maybe I've already one on my side. What were the most challenging aspects of your project?
I think the most challenging aspect of our project this year was working from home, to be honest. We were excited to have a group at Strathclyde to work in the laboratories and meet up, but unfortunately, due to the ongoing coronavirus pandemic this year, we actually haven't been able to meet personally until back in February of this year. And that was a long time into our project. We had to utilize Slack channels and OneDrive and Zoom meetings to have to integrate all our working together. And I'm sure the rest of the team would agree that it's been a very challenging aspect. One of the technical aspects that we worked on was the hydrogen fuel cells, which I know Rory had a lot of input in. Do you have anything you'd like to add with that, Rory?
With the fuel cells, it was mainly just about the safety and getting the cells somewhere safe to use them, and having the hydrogen there because there were obviously, with the safety aspects, you had to be in a well-ventilated space, no ignition, any source of ignition. So that was the main thing, of just having it. And that was one of the reasons why we decided to change the type of cell that we used, so that we didn't have to use both compressed oxygen and hydrogen. And we decided to use air, even though this isn't as viable for a moon-based system. We still thought that it provided a great system that showed off what they could do.
Thank you very much. Maybe on the fuel cell side, I have a question. Will it be easy to upscale these fuel cells?
So with the way the fuel cells are, there's what you call as a fuel cell stack. So our cell had 20 individual cells in it. So with upscaling it to a large scale, we estimated around 50 kilowatts, because it was mainly going to be used for power storage and like backup power. So this would just mean that we just have to have more cells and more larger cells. And but as you increase the size of a fuel cell, unlike batteries as a conventional method of power storage, the increase isn't linear. So as you increase the amount of cells, you can get a lot more power for what you're doing, whereas a battery, it's a pretty linear scale.
Thank you for the answer. I'm checking the question. I have a question related to your Origami like solar arrays. How do you plan to test the deployment of this large Origami like solar array on ground without the presence of microgravity? It's a quite complex deployment, if I correctly understand.
Yeah, it's a very complex topic. You see, our solar array deployment is currently just a theoretical and was designed mainly from a geometric perspective. We were attempting to achieve the required launching constraints and maximize the ratio between the deployed and stow diameters. We see next year's PowerHab team continuing on this trend, considering the testing methodologies that are currently used. When designing components for space, minimizing weight is absolutely essential, as this contributes mainly to cost. So on Earth, these structures won't be able to support their own weight. Therefore, next year's team would have to consider designing a ground support rig that would be able to provide the apparent weightless environment for each array during deployment testing. During our research, we took a look at NASA's recent Lucy spacecraft, which is an example of a current system which has successfully undergone solar array testing using a similar source special precision weight offload device, and that was employed inside a vacuum chamber for additional support. So it's definitely a topic we're mainly looking into in the future.
Okay, thank you very much. Concerning the wireless power transmission system, you selected a laser for the power transmission. Is a specific challenge of using a laser in space, a high power laser, as you intend to use it in space?
Yeah, so using the laser in space is definitely a lot more difficult than in Earth, just due to the scale of the laser that would be needed. But laser came with a lot more benefits over microwaves, just with the fact that we could scale down the full-scale system and also possibly obtain better efficiencies.
Okay, thank you. Concerning the nuclear fission subsystem, it's of course a very interesting solution for producing power on the moon, and for all space exploration, power fission is a very interesting power source. It's for sure technically feasible. Do you think it's also politically feasible as well? Did you address the political aspects in your trade-off?
As you discussed there, it's a very interesting topic, the nuclear fission subsystem. Unfortunately, Sehar, who worked on it, isn't here to discuss it in detail today, but I can say that what she did was performed a detailed HAZOP risk assessment, and that included potential safety concerns. This does involve political aspects such as the ability to look after the subsystems, and if anything did go wrong, it could fall into potential the hands of terrorists, or could anger other countries. So it was addressed, but unfortunately she can't discuss it in more detail today.
So thank you again. So it's really your topic is really relevant for space, but as well for us, really producing energy, distributing it, and storing it is really challenges we have had to address on space mission for sure, but on ground as well. So thank to PowerHab team. Is there any other question? If not, I would like to thank the PowerHab team. Also, many thanks to Mount Pilatus Bahnen, to Lucerne Verkehrshaus for supporting and hosting us, and of course to the whole space innovation team and to all of the people who supported this exciting project. And of course, many thanks to Swiss Space Office, which funded the activity, and to ESA, which initiated the activity and provided great support, mainly through experts. See you soon.